Hello, ladies and gentlemen. This is Mr. Hunter, and this is your electrodynamics notes, part one. So, as we talked about before, we just finished electrostatics, which electrostatics has to deal with kind of charges and freeform movement when they're not restricted to a wire. So, like what does charges do in the air, as well as when they're next to other charges, they make electric fields. Those electric fields exert forces on other charges, so on and so forth. So that, therefore, we deal with like the electrostatic force equation, and then the electric field equation, which is E equals F over 2. So now we're starting to deal with, okay, what happens when we have a movement of charge in a certain direction? And just like your do now stated with, if I had a wire, how would I get charge to move through the wire? Most of you had it right. You put a positive on one side and a negative on the other side, and the electrons are attracted to the positive, and so they move. So now we start with dealing with electric potential energy and electric potential, which is voltage. And that is actually, we start talking about electric potential, which is work. And work is the energy as a result of the location of a charge in an electric field. Case in point, if I have a positive charge in a positive field, if I want to move that positive charge closer, I have to do work on the charge, or AKA put energy in to get that charge to move closer to the positive field. So for example, here's my first example, right? And so I have this positive charge and it's emitting this positive field, and I have this positive charge right here. And in order for me to move it closer, I'm going to have to put in work. Remember, work is force times distance. So my force is in this direction, and it's the electrostatic force that I'm exerting times the distance that it's moving is going to equal my work. So like as I'm pushing this closer and closer, it's getting harder and more difficult because they don't like each other. It's pushing back because that other charge doesn't like each other. So, come on, show up. So text is supposed to show up right here, but it's not. So so that charge, oh, it's probably in the background somewhere. Let's see. Oh well. Anyways, it basically says that I have to do work to move this charge over to the other charge. So in this case, voltage equals work divided by charge, and by me doing some work, I'm actually creating some type of voltage when I'm moving that charge. Now, in this case, work is done. Essentially, the text that I had coming up is work is done. Why? Because positives don't like positives, or negatives don't like negatives. So I have to do some work to get that proton next to the proton. Like, think about it. If you have two younger siblings that absolutely hate each other, like if you ever want them to stand next to each other, what do? You got to shove the other one over to stand next to the sibling because they won't move. And so they're like resisting you putting them over there. Okay, so let's look at the second situation. I have a positive charge with a positive field, and I have it next to an electron. Is any work done? No. There's no work done because I'm not exerting a force in the direction of distance, and I swear I can spell. My spelling has been just terribly off today. So, no work done. Why? Because electrons like protons and protons like electrons. So this guy is going to move towards here because they like each other, so no work is done in that situation. But work is done when I have two positive charges because I have to put some energy in to get that to move. In that case, I actually make a voltage. So let me go back to Zoom. So now, since we're now dealing with movement of charge, the movement of charge in a specific area, I'm going to go to the middle column, is actually called current. And current, as we defined in class, is how fast the charge is moving. Or as I said it in class, is how much charge we have per unit time. Or time. Ugh. Charge per unit time. The struggle is real today. So, how much charge per unit time? Let's see if I can get this to recognize my writing. So how fast the charge is moving and how much charge per unit time. So if we look at our reference tables, we see that the symbol that we use for current is I, so that's the symbol for current, equals delta Q over time, where Q is charge, which we measure in coulomb, divided by time, which is coulombs per second, and that actually equals amps. So we use, it's actually ampere, but we say amps and we use the letter A. So I'm not going to make you copy it down here. I will mention it here. In class, I gave you an example and said, hey, if I have, one class actually gave 31 million. If I have 31 million elementary charges and it's moving past this one point in 0.005 seconds, what is my current? And so what you had to realize was, I don't have the charge. I know how many charges are moving, so you had to multiply that by the charge of one elementary charge, which is 1.6 times 10 to the negative 19. So I multiply how many I have by how much it takes for just one of them, and then I divide that by the amount of time. We got a really, really small number, because current technically is kind of small. As I mentioned in class, if you were to actually get 1 amp of unrestricted current to move through you, it would liquefy your body. 1 amp is really, really dangerous. Let's see, another equation that we have that deals with current is called Ohm's law. Ohm's law is voltage equals current times resistance, but if we solve that for current, we get current equals voltage divided by our resistance. And remember, the unit is amp. So that's Ohm's law, which voltage is proportional to current times resistance. Or if we solve it for current, current is inversely proportional to resistance. So it's voltage divided by the resistance. Okay, how am I doing on time? Doing pretty good. Okay, so resistance, if current is how fast the charge is moving, or how much charge per unit time, then resistance, or as I like to say it, resistance is the ability to slow or stop the electrons. Oh, I should say charge, stop the charge, because technically you can have protons moving, but it's really, really hard. Remember, electrons move a lot easier because electrons are 10,000 less massive than protons, which means they're always the ones to move. So the ability to slow or stop the charge, and the unit is the ohm, which that's the symbol we use, and it's the Greek symbol omega, and then it is the ohm. So that is the unit of resistance. And so once again, we have two equations that deal with it. We can solve Ohm's law for resistance, and we just get voltage divided by current. Or if you look in your equation, your reference table, there's another equation where it says resistance equals a weird-looking P, which we call rho, multiplied by the length divided by the area. That's actually the resistance of an object or resistance in a wire. In a while. Wow, I'm sorry. Anyways, I hope this is amusing to you guys. So the Greek letter rho looks like a squiggly P, and it means resistivity. Resistivity is the natural resistance of the wire, and the unit is ohms times meter for resistivity. Don't forget to show that when you show LEPA and list your things. I remember on the test last year, you had to calculate this equation, and a lot of my students left off ohm times meter and lost points there. Length is just how long the wire is, and the unit for that would be meter. Wow, I can spell, I swear. And that's meter, and then area. Now, a wire makes the shape of a circle, so the area of a circle is pi r squared, so the unit would be meter squared. So we're going to be doing a lab in class called Resistance in a Wire, where you guys are going to be using Ohm's law, and you're going to be using resistance in a wire to find out the real resistance on the resistance boards and compare it to using Ohm's law. Let's see, and it is exactly 10 minutes, so I will stop there and I will pick up on next time. So make sure you bring in this into class so that you can get a grade. Have a good one.